Hi, Carl. How are you today?
Great. Thank you.
Good. As I mentioned, I wanted to follow up on the great presentation you did about your approach to teaching and ask a few follow-up questions that'll be interested in the community of Kata practitioners that you've learned a little bit about. Personally, I've been a teacher of industrial engineering for 35 years at University of Michigan, and uh, frankly, a lot of the teachers who are researchers at university care more about research than teaching. And hearing from someone like you, who's won a Nobel Prize and is a renowned physicist who cares so much about teaching, is really impressive, and really appreciate it.
Thanks. But I always like to emphasize I actually care about learning, not so much about
I
teaching.
see. Okay.
It's a subtle but quite important distinction.
Okay. But you care about other people's learning, not just
I
your own.
care about other people's learning, yes.
Right, right. Good. No, that's good. A good distinction. What was your just first impression of learning what Mike is trying to do with this idea of an improvement kata and a coaching kata?
Uh-huh. So, I mean, to be honest, my first impression was it was a little hard for me to grasp in this kind of context-free
Right, right,
situation.
right, right.
But it did seem very consistent with everything, the research I knew on this development of expertise and the
Right,
development
right,
of improved performance,
right,
the the idea that as people level of mastery, if they're following this approach, as their level of mastery improves, they're also better able to kind of evaluate their own level
right,
and
right.
guide their own path forward. So that's all, like I say, very, very consistent with all of,
Good. Actually, I'm going to break from the script and just ask you how you got into this, because the natural thing is to teach the way you were taught and stand in front of a room and lecture about physics.
yeah. So I mean, I had actually had a strange education in my own way. I didn't take that many courses. I spent lots of times working in a lab, but the way I got into my work in education was not through teaching. Actually, it was through working with graduate students in my lab and trying
Okay.
to understand their development of expertise into being thinking like physicists and understand why they're having many years of great success in courses had very little to do with whether they could do physics or not.
Okay.
And trying to understand that really as an intellectual problem was what got me digging into this and changed the whole way I thought about teaching and learning.
Okay. So you had a direct experience that caused a puzzle or problem in your mind, and you started to try to solve it. But apparently, along the way, you learned about what others wrote in cognitive psychology and brain psychology uh, that helped you explain maybe what was wrong with what you were
I,
doing.
yeah, absolutely. And it also got me involved in actually doing research studies in this field, which I did
Okay.
for decades and still do.
Okay. How long ago was it that you discovered this field of cognitive brain psychology and started doing research in this area?
Uh, I mean, particularly as thinking about applied to physics, probably getting close to 30 years
Wow.
ago.
So you were in parallel doing physics research and this learning cognitive research.
That's right. I had two parallel research groups. One is blasting atoms with lasers and that stuff, and then the other one was actually doing research studies on how people learn physics and doing experiments and teaching different ways and seeing what thinking they learned.
That's a little bit odd because you're usually professors have one specialty and they become known in it, and that's what they hammer away at. And you're off in this totally different area from most physicists.
Yeah, but I mean, I like to make the point that these things have very similar kind of intellectual bases.
Hmm.
Because the things I want people to learn and the things I do research and things I figure out how to measure are thinking like a physicist. Okay, so
Okay.
that clearly carries over a lot with the research, but the kind of experiments that I do, I mean in both cases where you're really pushing the edges of what we know,
Hmm.
it's all about lots of unknown variables and sorting out what's the important variables, what the unimportant ones are, doing good experiments that give you clean results in the presence of unknowns.
Okay.
So you see, it's not so different.
Well, so there is this body of knowledge and theory and from brain science and cognitive science uh,
Yeah.
that you drew on. Could you give a couple, maybe a specific examples of findings from that body of research that's informed your experiments?
Yeah, here the challenge is to keep this in less than
Yeah,
45
right,
minutes.
right, right, right. Okay,
Because there's a great deal, but I'll pick a couple that particularly kind of touch on the
right,
kata
right, right,
work.
right,
Uh, so one of the most basic ones, though, is the idea of working memory and cognitive load. This is the idea that the brain for short time scales, like a discussion like this or a class, the brain has this very limited capacity of number of things it can keep track of and pay attention to. And it has a so-called short-term working memory is
right,
what's
right,
dealt with that. And the more you load up that working memory, kind of the less capacity there is for thinking about and processing and learning. And
right,
so,
right,
and so there's this very basic but easily overlooked fact that you just need to, if you want somebody to learn something, you think very hard about not overloading
right,
that working memory. And so that means, avoid complicated figures that have superfluous information in them, avoid the use of technical jargon, etc. Uh, and that just frees up capacity for them to think. So that's one very basic thing that
right,
I
right,
find shows up
right,
over and over in any discussion,
right,
even.
right. No, that makes a lot of sense. Uh, my department I'm in, most of the faculty are basically mathematicians, and they're teaching optimization algorithms, and they have a whole set of topics that make up a course. And there's prerequisites for that course, and then in that course, they have to cover these 50 topics, or the course wasn't done right. And so the problem that they would face in using your methods is they'd be concerned about is to simplify this cognitively so I don't overload the students, I might have to reduce some of the topics. And they just hate that idea. And now, of course, the students aren't really learning what they're saying, but they
Yeah,
think they are.
right, right. And I mean, we've done studies on that, and I'll talk about it. I want to give you one other area
Okay.
of the cognitive science
Okay.
that I really rely on and actually goes very much to the heart of this, of the uh, Toyota Kata work, which is the ideas, the studies of expertise, and how experts in high performing individuals in
Right.
these
Right.
fields, uh, any field you can sort of quantify performance. They see that there's very particular ways those experts think and have learned that expertise, and so they have this for specific to the field. They have these very sophisticated uh, mental organizational structures by which they organize all the
Right. Right.
information.
Right.
And so when faced with new problems, they can call on that information in a
Right. Right.
very
Right.
meaningful, effective way. And so to me, that's been one of the things that I focus on a lot with teaching, of thinking, okay, how can you have the learners sort of not see these as a bunch of unrelated little pieces of
Right.
information,
Right.
but are
Right.
linked together in a useful way, and they can and it guides them as to when and how to use that information, not just memorize it for tests,
Right.
etc.
Right.
And so that thing goes to the point that you're talking about with, oh, I got to cover all this material in
Right.
lecture so
Right.
that and that sort of thing that you just, anytime you collect data on this of what students take away from an actual lecture like that, the more that's covered, the less they take away, and it's really tiny what's happened. So this is just I think, well, I know that the standard lecture approach, it became technology made it obsolete. But in this case, the technology was the printing press, not the computer. And people just have, but because it was kind of a religious tradition, they've come to rationalize why it was effective somehow in total absence of data. And we've had some spectacular experiments that caught quite a lot of attention when we had lecturers who were so sure they were doing a great job and they let us actually do measurements and comparisons and showed it was just dismal. So
it's interesting. It's interesting that these people we're talking about are scientists, but they're not used to the idea of applying science to what they actually do, how they actually teach.
Yeah, and that's actually one of the places where I disagreed some with what's in Mike's book on the Toyota Kata, of saying this kind of scientific thinking that it's meta, that it applies in many different situations. I think that's wrong. I mean, the research would say that's wrong, is that the application of something like this is so dependent on your prior knowledge about that context that it doesn't go. And the example you gave is a perfect example of that, how these scientists just are turning off it's not fair to say they're turning off their brain. Right. They're just not getting turned on when it comes to thinking about teaching and thinking scientifically.
Right. So let's get back to that about the kata. So the idea, what Mike's introduced, is that in the workplace, and we've been working in this field of lean manufacturing, and it goes back to Toyota, and there's a bunch of tools that you implement to create better flow, to improve productivity, to improve quality. Mm-hmm. And then what Mike was noticing is people kind of mindlessly using these tools and didn't really understand why they were using them. And as a result, they used them poorly. And then once they had implemented them, they checked off the box, we're done. And they didn't then continue to evolve them and change them and adapt them and learn from them. So he was trying to come up with a countermeasure to that, to kind of force people in the workplace who don't think of themselves as students or scientists to take the time to think about their objectives, think about their current condition, think about what they're implementing as a set of experiments instead of as a set of solutions. So it's kind of a simplified version of the scientific model for working level people, but it's a big stretch for them to think this way.
Yeah. And, what it actually matches very closely within the work in cognitive psychology is the process by which the research is seeing the development of expertise, where you have to continually to progress into a higher level of expertise, you essentially have to be continually questioning your level of mastery, looking for challenging things to tackle and doing that. And so that seems to me to have essentially a perfect overlap.
Well, the original model that we often talk about is the Master Apprentice model. And in Toyota, for example, when they just started learning about cars, they had to learn how to machine an engine part and how to make a transmission work. And they got used to the idea that they developed these kind of master craftsmen who then took as apprentices the young people and taught them one-on-one. And then we kind of lost that in most of the world.
Yes, but it's also true that in many cases, I think the Master Apprentice doesn't fully capture what's important here. Okay. What this is taught, the master sort of shows the apprentice how to do something and tells them how to. This really also captures, though, the idea of the apprentice going on and continuing to improve, if you like, right? And there, the research in the cognitive psychology shows a lot of the comparisons between people who sort of reach a certain level of mastery and decide that's good enough. Stop looking to how they can go beyond that. Where there's others who go way beyond what any master can tell them. They doing these kind of kata, the equivalent of the kata exercises. So
in fact, the students, the learners, have a lot of knowledge already of their processes. They've often been working in this company for 30 years and they've been running this machine. And then people who have learned the basic concepts of this kata go in and they work with these people. And within a few months, they've doubled the capacity of the machine and using their existing knowledge that they didn't know they had. But they weren't, like you said, they kind of peaked out and they weren't questioning anymore. And the person doing the teaching doesn't understand anything about that machine, but just by using this process and asking them questions and challenging them and getting them to experiment, they go to levels that they never thought were possible.
Yeah. And, the difference in the kind of teaching I do, that the coach or teacher actually always knows way more about the machine than the learner ever could. It's sort of an inverted process. So they're also, as the learner's primed, giving them the information about the machine. But but a lot of the same kinds of structures, the same kind of thinking has to go into the brain of the learner.
So the way that, and this is not just Kata, but in the whole lean community, it's sort of accepted, and it goes back to Kata and the original founders of this. It's accepted that you want to challenge the learner to think. Therefore, you don't want to give them the answers. So you ask a lot more questions than you talk. But you have this body of knowledge, and you need to communicate the body of knowledge. And at the same time, you want to challenge them to think.
Yeah. And so, in the kind of teaching we talk about, there we do have the teachers do a fair amount of talking, okay? Because the learner doesn't have that knowledge. But what's really critical is that the learner is first primed to learn from what the teacher, coach, etc., has to tell them. And so that takes instead of the usual order of I walk in and tell these sort of numb students a whole bunch of information that they have no context about, no reason to understand it, no reason to see it's important, I give them some problem to solve, and they struggle with that problem. It's carefully designed. So then they're really primed to learn from, they understand there are certain key things they need to pay attention to, information they need, and then, I tell them and they, get a lot out of it. There's some great work by Dan Schwartz where he sort of has students do the same thing, but in the opposite order, being told, a lecture, then practicing that, sort of the standard, versus practicing trying to do something that they can't actually do, but they can engage in it, and then being told. And there's sort of a factor of 10 difference in the amount they learn in those two things. So that's a very spectacular demonstration.
So how does this relate to the kind of law school or business school practice of case study teaching, where the student analyzes the case and they come in and they're called on and they answer the questions?
So that actually can vary. The details about what you call on and whether whether the faculty member is just using the questions to make students squirm as kind of a structure for their lecture, or whether it's actually involving the whole group in a thoughtful analysis, can be so different that I don't want to make any generalizations, because I've seen it done in different ways that you'd almost label it the same, but realize not what's going on in the student's mind is a totally different thing.
But the basic concept that you have a real problem, you struggle with it, and then that would open you up to learning.
Yeah, and the kind of problem you need to be given is something that you can recognize what's important about that context, and so the Kata is talking about what the goals are. Okay, so what's important about the structure of the goals? That's all very consistent.
Okay, so talking about the Kata with the goals, you start with a big challenge for the company. Like we want to double one company that I've been working with. They want to double their capacity because their customer wants double the volume, and they don't want to buy any more machines. And they're working toward that challenge step by step, experiment by experiment. They're making great progress, and they're amazed. I'm I'm kind of amazed. But anyway, that challenge is, say, a year out. So they have a very clear challenge. And then they have short-term goals that might cause target conditions that are like 2 weeks out, so that they don't, and we tell them, don't worry about the challenge. It seems overwhelming. Don't worry about it. Focus on the next target condition. Then we'll, at that point, define the next target condition based on what we learned. So it becomes an iterative process. Is there something like that in your teaching where you have a vision for the students and then you have these shorter term goals?
I mean, I have that, but it's in the kind of things I'm thinking of. We sort of always know the long-term goals,
I see.
because we're trying to. That's one place where I really sort of see it as different, because we sort of are taking this great body of scientific knowledge that's been developed over a couple of hundred years, and we're trying to have students sort of absorb, reach that. And so we're sort of bringing in the expert of, okay, what do we know, and then how do we have the students work their way up to that? So it's a little different, because, in your case, I'd say, if I was kind of trying to think it in those contexts, I was thinking, well, yeah, I could take a goal if I want to make a faster than light rocket ship that takes, runs on a flashlight battery. But I can break it down a lot of little pieces. I'm not going to get there. So.
Right. Yeah. Well, there are projects at the University of Michigan. There's a solar team, and they often win, and they have to develop the solar car, and they are more like that. They can start with a challenge.
Yeah.
So the idea of shorter term targets, though, for example, you can do quizzes, you can do tests, you can do papers. Do you try to create intermediate products to challenge them?
Yeah, absolutely. That we design this with, we've got some top, major goal we want students to master, and I'll take in a great big class, for example. And so I would think of, we oftentimes use these clickers, little electronic response systems all the students have. And so we'll start out with pose questions to the students, and they have to try and think of the answer and think of the reasoning. And then we'll actually, before we tell them anything, they'll have to talk to each other. It turns out that process of trying to explain your ideas to somebody else, or teaching them, and also the mental process of evaluating the validity of somebody else's ideas. Those are all things that give you really, you're practicing really important aspects of thinking in this. Through that process. And so they've struggled with the ideas, they've thought about them in a variety of different ways, argued over them, and then you'll go in and then you'll tell them. But I should point out, we run around and we listen in on them while they're having those discussions, so we can be much more targeted in the feedback we give them. So it's kind of like the one-on-one tutor, except I'm trying to put that in place with 200 students.
I know, which is tough.
And so that's, and we'll have, through these sets of questions, problems they have to solve, we will, work through then to the ultimate, the big goal of those pieces fit together.
So given what you know about cognitive overload, and given that there's a fair amount of time spent on doing these activities and discussing it and all that, do you have to whittle down the number of concepts you're trying to teach to a smaller number?
No, not usually. It can vary with the course, but usually, we just think very carefully about how to optimize the use of time. So, this is somebody working with companies can understand better than academics. But so you say, look, class time should never be spent just giving simple transfer of information to the students. That's something they can get outside of class. They don't need the instructor. So push all that outside of class, and then pick the key things that they can learn, the sort of most challenging aspects of thinking when they're in the class. They can interact with other students. They can get this immediate feedback, and then you can have them do homework and so on that prepares them to actually cover new material, but they've got the tools to master that. And so we find just by shuffling things around of where they do different things and essentially an optimization algorithm of time use and learning, we can cover pretty much the same things.
Right. Okay.
And more importantly, the students learn a lot more.
Yeah, that's right. Does that work better? I can argue that that's great at Stanford when you have so super motivated, very intelligent students, but at a average college, they may not be very good at self-learning.
No, actually, if anything, it's probably better. It probably works better at the lower levels. I mean, we have research. We do. I mean, my own group is. I've done a bunch of research in Colorado, at University of British Columbia, Foothill Community College. We run studies at, as well as Stanford. In some ways, it's a little less clear at Stanford because the students are so used to going off and learning things on their own, whereas these other places they can't, and you see a bigger impact. But the reason there's a real reason why it seems to be, our data shows, and lots of other people's data, it benefits all the students, but it benefits let's say the less prepared ones a bit more. And it's because it really structures the learning process in a more explicit way. They're less prepared. They're also less prepared to know how to learn as well. And this kind of makes the good learning process much clearer and cleaner too. So
it sounds like a lot of work for the teachers. When I got to Michigan, the people who taught these math-based courses, they had yellow notepads, and they had all their lecture notes, and they would copy them on the board. And the way they taught is, the first year you have to create those yellow notes, and then the second year you refine them, and then you just are on automatic pilot. So this sounds like a lot of work to them.
Well, in some ways it is, but before I got to Stanford, I ran this program at British Columbia and Colorado where we changed something like 250 faculty members teaching in a major way. And virtually none of those are willing to go back. Okay. It took them time to learn how to teach this way and develop the materials in the same way. It takes quite a bit of time to fill up those yellow notepads. But once you do, it doesn't take any extra time, and all the faculty who try it find it just so much more rewarding, rather than talking to a chalkboard. You have the students are really engaged. They're really interested in digging into the subject. They're calling on your real expertise in the subject, and that's just so much more rewarding way to teach for faculty that they, that it's actually, it's like I said, they never switch back. It's just a question of getting them over that hurdle of the initial investment in time to learn it.
Okay, so this is it's kind of a big deal to change the way you think about teaching when you've been taught this way and you've been teaching this way for 30, 40, 50 years.
And it's been a tradition for 2000.
So you're trying to make major change. How is it? What are some of the things you've learned about managing the change process?
There's a couple of things. I mean, first big part is this is very much like change in any other organization. When I got into trying this, this experiment at UBC is really the only large scale experiment in changing teaching across the university. And I talked with John Kata, who from Harvard, who's done a lot of work in organizational change, and read his books, and boy, everything he said, I was skeptical applied to universities because it's an industry, and And whenever I talked to people about it, they were sure it didn't apply to universities. And now that I've tried it, it's all true. It's a groups of people. The one really big challenge and outstanding in all of this is to get the incentive system right, because right now people just don't the evaluation of teaching, I'm sure you have it, is student course evaluations, and they just aren't very meaningful. They as an evaluation system, as you would want in any organization, they just fail on almost all counts. They don't capture the best practices. They don't guide improvement, and so on. And so that's the place where I see is the major issue, that as soon as people have to have more meaningful evaluation to actually have something that moves us forward.
Okay, so you've talked about that and how there's ways of measuring what people actually learn in a class. What are some of the ways? That sounds like it's somewhat specific to the topic.
Yeah. And so actually measuring what they're learning in class, that is topic specific. And so that's hard to do. What isn't hard to do is to measure if the teachers are following certain practices that are more effective.
Okay.
And so this kind of goes back to, what you do in the medical profession or what you do in an industrial thing. You can't go in there and evaluate in detail every car and how the bolts are put in, but you can see if people are following the best practice of keeping track where the bolts go and how they turn them and so on.
Well, the way that it's done within Toyota, which is more rigorous than most, is they have what they call standard work, and then they have audits where the supervisor is doing formal audits, and they have paper and pencil, and they're doing this on a regular basis, rotating from team member to team member, and they might watch you once a month. And then when there's gaps, then they have discussion about whether maybe the standard work is wrong or should be changed, or whether why are you not following this? So it leads to a dialogue and it leads to learning. Other companies will send in teams of auditors to a plant less frequently from the corporate office, and they'll have somewhat rigorous things that are easy to measure. And then they'll say, you're doing all these things wrong. And it doesn't usually lead to learning. It leads to compliance.
Yeah. And, and a big part of this, so part of that is something that universities really haven't touched yet, but also just the mere fact of thinking hard about, okay, what's the best practice to do in this particular situation? What do we know from research and studies say, and so we sort of have to get that into the culture.
Right. Well, I think personally part of that is that you have to actually have people walking the classrooms and watching, and then have a dialogue and not just rely on numbers that pop up.
Yeah, I think that's right. Yeah.
Okay. Yeah. And is this filtered into your PhD mentoring or your graduate student mentoring? Do you do anything different in the labs than you would have done 30 years ago?
I'm sure I do. The question is, what is my memory of what I did 30 years ago compared to what I really did? Right. So I need an outside observer. But no, realistically, it's somewhat the same. Although, I have to say that even back then, the kind of teaching was what we see now. And I think graduate teaching in general was a lot better aligned with what we know is effective, which was much more this Master Apprentice thing where I was, giving them tasks and see how they do, and then checking in and giving them feedback on it. So.
Right. Great. Well, it's a pleasure to talk to you. I'm sure our audience will appreciate it.
Okay.